Okay. So maybe we can get started with the talk. So this week we're lucky to have Zilinghan Li presenting. He's a machine learning engineer in the data and science learning division at Argonne National Laboratory. He holds a Bachelor of Science in Computer Engineering from Zhejiang University in China and a Master of Science from UIUC. He's the lead developer of advanced privacy preserving federated learning framework, which we'll see a demo of today. And he's deeply engaged in developing AI models for biomedical and scientific applications, including frontiers of data-driven discovery. So today Zillian will be giving us a demo of the APPFL framework and demonstrating some of the new tools and integrations with MONAI they've developed. I'm very excited to find out more.
Yeah, thank you for the introduction, Pernice. So let me share my screen and get started. Just confirm, can you see my screen now? Okay, thank you.
Yes.
Yeah, so hi everyone. My name is Zilinghan. I'm a machine learning engineer at the Argonne National Laboratory. And in today's tutorial, I will briefly talking about the integration between Argonne's advanced privacy preserving federated learning framework and its recent integration with MONAI. And at the beginning, let's briefly talk about what this integration is about. So MONAI has an FL module, which provides a MONAI Algo class. And this class contains train, evaluate, and get weight function to enable federated learning by leverage a collection of medical imaging model available in the MONAI bundles. So with this integration into Apple, you can actually use all of this medical imaging models to do federated learning in our APPFL framework. So, I mean, we need to give a great thanks to MONAI. And on the other hand, what can APPFL provide to MONAI users and what kind of capabilities we can provide is something that I want to share in the next. So what the framework can provide really depends on what kind of challenges are, present in FL, and we are trying to provide various solutions to different challenges. So what are these challenges? First, in federated learning, it is not like traditional distributed computing where you just partition a centralized data set to different machines and do training. In federated learning, data are collected by different geographically distributed data silos. And this data are usually heterogeneous with different data distribution. Data may form different clusters at different sites. So with this heterogeneous data, when each client are training their local model, they may drift away from each other. So when you do global aggregation for this drifting away models, the performance of the global model may degrade due to this drifting away, the client drift problem. And also, in federated learning, the clients are really distributed and they have very heterogeneous compute and infrastructure. Someone may use like on-premise HPC or computing clusters. Some may leverage some cloud computing. They have different computing capability, and they may have different structure and system settings and so on. So this poses some other challenges in setting up the federated learning, as well as some challenges in the efficiency of the algorithm. So we will talk about more about it later. And there are some malicious attacks in federated learning due to its distributed nature, because in federated learning, you cannot get direct access to client's data, so you cannot monitor or inspect client's data. So it is possible that one of the federated learning client wants to be an attacker. It may train using some wrongly labeled data or just noisy data, or it's just train on normal data, but it will send you a corrupted training model. With one corrupted training model sent to the server for aggregation, the performance of the aggregated global model will definitely degrade a lot. And also, as we know, what is the main motivation for federated learning? It is actually one of the main motivation is actually for privacy preserving, because in federated learning, we don't share data directly. We only share model parameters because we don't want others to get access to my data. So that's one of the main motivation in federated learning. But federated learning itself, it's actually not 100% privacy preserving. With access to the exchange model parameters, you can actually do data reconstruction to reconstruct the training data. So this is another kind of attack to federated learning, and we want to avoid that. And also, we know federated learning is distributed, and its main area of application may be in biomedicine, in finance, and these domain experts may not have the expertise to really actually set up federated learning easily. So the setup can be tedious. So what are our solutions? What are the solutions provided in our framework to resolve this? So first, for heterogeneous data, the first type of solution is actually utilizing some server-side momentum or other optimization to avoid drastic changes in global model. Some examples may include federated average with momentum, fed-adam, fed-adgrad, and fed-yogi. So let's just see a brief example. So for traditional federated learning, it actually just takes the gradients sent by different clients and do a weighted average, and use that gradient to update the global model. But in federated average with momentum, it actually applies some momentum update to the global model to just to make the global model don't change too much, so that this can alleviate the client drift problem a little bit. So a second side of solution is actually leveraging some proximal term or variance reduction corrector in client local training. And this is to prevent local training, the local model drift too far away from the global model. Some examples include scaffold and fedprox. So in scaffold, we can see that scaffold kind of predicts what is the client drift in each local training, and it just consider this client drift, or it just try to reduce this estimate client drift in the loss function or in the local update. And in fed proxy, it actually adds a proximal term to make the drift from the client local model and the global model not too large. And the third set of solution is that you can actually inspect the data quality before federated learning to exclude some sites with extremely bad data or outlier data, or at least you can exclude some bad data within each site. Or you say at least if you don't want to exclude any data because you want some more general data, and you want to apply solution 1 and solution 2 to alleviate that, this can at least provide you some insight to reason about why my final model have this performance. So actually in FO, we can enable the user to generate some data readiness report to give a visualization or some statistic summary for different site for the data from different sites, and this will not review any sensitive information of each site. So now let's move to heterogeneous and compute infrastructure. As the computing capability of client machines could have very large variance, different clients may take a significantly different amount of time to finish one local training epoch. As a consequence for that, for synchronous federated learning algorithms, such as the very base federated average, where the server has to wait for all the clients, or say a selected group of clients to send local model backs, they will suffer a lot from resource wastage. So let's just see a simple example. Suppose I just have two clients. Client 1 just have a very weak machine, and client 2 has a very strong cluster. And when the server, when they are performing their local training task, client 2 just take 15 minutes to finish, while client 1 takes an hour. But the server will only returns back the global model after receiving the clients from both sides, and to proceed the next round of local training. So you can see that the powerful client 2 are wasting lots of resources, and it's actually not very efficient, and this is not what we want. So asynchronous federated learning algorithm, which actually updates the global model immediately once receiving a local model from each client, or say a group of clients, it can improve the efficiency of federated learning in heterogeneous computing environments. So in last year, ICR 2024, our group also proposed a state-of-the-art asynchronous federated learning. It is called FedCompass. And the underlying idea behind it is very simple. So suppose that by using some tricks, the server can get an estimate of the underlying computing power of each client. Then they can simply assign the number of local training steps proportional to the underlying computing power. And with that, different clients can actually finish their local training almost at the same time. So in this case, we can avoid a lot of wasting time, a lot of idle time for each client. And it turns out that FedCompass can make a lot of applications converge much faster than Fed average, and it also alleviates it also resolves some other issues about asynchronous algorithms compared to Fed async and Fed buff. So if you it is already integrated in APPFL, so if you are interested, you can take a look at it and to train your MONAI model. And the third type of attack, which is malicious attack. So we know that some clients may try to attack the FL training process by sending poison updates for aggregation. To resolve this problem, there are some algorithmic solutions, which include like using some small central validations dataset to decide whether to drop certain clients' updates or not. And some other algorithm may check, like may compare different model parameters and exclude outlier model parameters. And in system level, it is also important to build some secure and trusted federation with user authentication system. So if you can use authentication and invite all the users you know to do federated learning, then you can significantly reduce the risk of malicious attack. In APPFL, we also support some authentication, and user can also easily integrate their custom authentication. In terms of data reconstruction, as we mentioned before, it's another type of attack to federated learning, because federated learning itself, even though no data is shared directly, it is not actually privacy preserving. The training data can be reconstructed from model gradients. But thanks to differential privacy, which actually you can think it's just add some noise to the model parameters, can significantly reduce the difficulty of reconstruction. So this image actually comes from one of the paper from our group. So if you train a model, use the model parameters without any differential privacy applied, then you can kind of reconstruct a very good image, like chest X-ray image from the model parameters itself. But you start to add more noises by decreasing your privacy budget, you can see that the reconstructed image quality is decreased and the reconstruction loss is increasing. And someone may not ask, yeah, definitely, yeah, adding noise can make the reconstruction much difficult, but it will also affect my global model, right? Because you are adding noise. So how should we do it? So in APPFL, we do support some privacy preserving algorithms. And why we say it's privacy preserving algorithm, because these algorithms are more robust to the noises we add during differential privacy. So if you see that on the right-hand side, it is Fed average with differential privacy. As you decrease your privacy budget, which means that you add more noises to the model parameter, the performance of the global model get decreased and decreased. But for privacy preserving algorithms, even though we are adding more noise to the exchange model parameters, we can just see very, very tiny impact on the global model performance. So if you really want to use DP to further protect your experiments, maybe you can try our privacy preserving algorithms. Okay, then for cumbersome setup, so we just list a few problems that exist here. So, due to distributed nature of edge learning, it can be tedious for domain experts. The coordination of distributed training can be tedious as well, especially for sites suppose you are using HPC and your HPC have certain scheduling system. And when you start a job, you may not get your computing resources immediately. So suppose you have 10 clients, they are international, and some of you are using a scheduling system, and you want them to start their local training almost simultaneously. Such coordination is very, very tedious. And also, because we are a national laboratory, we have a lot of considerations on HPC, and for a lot of HPC, especially from government national laboratories, it has very strict network access, and a lot of compute nodes does not have direct internet access. Then how can we use that compute node to do federated learning is another problem. And also, as we are trying to use federated learning to train a larger model, some people may say, okay, I want more efficient data transmission to not making communication a bottleneck for our federated learning experiments, and so on. There are a lot of difficulties when you are really setting up federated learning in practice. And in Apple, we alleviate those issues by supporting a versatile communication stack. So let me just give you a short example. Say for problem 3, like the compute node, that if it does not have network access, our solution is that we can set up kind of like a proxy on the login node of the HPC which have all internet access. And the compute node actually first talk about the proxy, and the proxy will help the client to talk with the server. So we support our communication stack is pretty comprehensive and solves a lot of these problems to make federated learning much easier for different use cases. So, okay, after talking about all these problems we are trying to resolve, and here is our design that we propose to resolve this. So in federated learning, we just create an abstract agent for both federated learning server and federated learning client, and both of them are initiated with some configurations. On the server side, you have a privacy module and an aggregator module they work together to do privacy preserving aggregation. And the scheduler on just sit on in front of the aggregator module. It will actually interact with the communicator to decide the synchronity of the federated learning. If it is synchronous, it will actually gather all client local models before passing the local models to the aggregator. If it is asynchronous, it will pass it directly into the aggregator to update the global model and return it back to the communicator. And if it's flat composite, it has more complex scheduling algorithms. And on the client side, it has a data loader to load client private local data, and an optional inspector which can use to inspect the data quality or data distribution for all the clients before you really do federated learning. This can give you some insight of how you want to do the training, whether you want to exclude certain clients or what else. And after that, we get the privacy module and the trainer module work together to train a local model in a privacy preserving way, if you want to use privacy module, definitely. And then in the communicator stack, it has a task controller, which is basically used to exchange tasks back and forth between server and clients, like what the client want the server to do or what the server want the client to do. And then optional data connector, which integrates a lot of additional data transmission protocols, so you can choose whatever work for your case to exchange large model parameters more efficiently. And it also comes with some lossy and lossless compressor. So this can help you to reduce the number of parameters you need to exchange between server and client if you are in a in a poor network and you are okay with some performance loss to use those compressor. So yeah, that's pretty much all we have. And to get more information about our framework design and details and how we really resolve those problems, what kind of algorithms we support, you can check our pre-printed manuscript. And our code is open sourced on GitHub. You just need to search APPFL GitHub, and you can find it. We always welcome issues and contributions from the large community. And APPFL comes with very detailed documentation, which starts from how to install it easily, how to launch your very first fetch learning experiment on your personal computer, and there are more advanced developer guides as well. And our fetch learning framework is also supporting a web platform services. It's available at service.appfo.ai. It is mainly designed for domain experts who really don't have like some computer science background, and this can help them to just configure federated learning in some web-based form, and it will also launch the server automatically for domain experts to interact with their local computing resources to do federated learning. It is fully based on APPFL framework. Okay, let's now revisit back to this FO to MONAI integration after we talk about what FO can do and what benefits we can provide to MONAI users. So as we mentioned, like now the MONAI algo help us to leverage a lot of MONAI, like a lot of medical image models available in MONAI models. And here's how we do it. So actually, we are defining a new class in our training module by leveraging the MONAI algo class. And here is a very brief description of how we do it, how we define this MONAI trainer. So I would say thanks to the awesome interface provided by the MONAI algo, it just takes about 100 lines to use all MONAI bundles in AppFo. So here's how we do. In init function, we just create a MONAI algo instance and initialize it. And in get parameters in get parameter functions, we just leverage MONAI algo's get weight function. In train function, we just leverage the train and evaluate function to train our local model and evaluate it before sending back the local model to the server for aggregation. And as we mentioned before, AppFo user can use MONAI bundles, and MONAI user, they can also use AppFo's different features and solutions to various federated learning challenges to federate their model training. So this integration, we already wrote a detailed documentation to run AppFo using MONAI bundle. You can actually just find it out in our documentation. And here we show a sample log from the experiment. So you can see that during the experiment, the server will receive the following metadata from the client, such as what is the current round, what is the validation accuracy, and what is the validation accuracy before training, what is the validation dice loss, and validation dice loss before training. So Apple will log all this client local training statistic on the server side, so the server can get a better idea of the training process. So at the end, we will provide some useful QR codes. The first one is our AppFo repo repository, and if you are interested in that and you think the solutions we provide could be useful for your future research, please leave us a star. And we also have a Discord channel for future discussion. If you have any questions when you use our framework, you can either raise a GitHub issue or join our Discord channel, to reach out to me and other developers. And at the end, I would like to specifically thank Praneeth and Holger for their advices and suggestions to all the amazing integration between Apple and Holger. We really, and MONAI. We really love this. We really love this integration, and we hope that we can further improve it and for more use cases. Here are some references for this talk, and thank you all for your time and patience listening.
Thanks so much, Zilinghan. Are there any questions from the group? I'm curious, would you mind walking us through a little more detail, maybe walk us through some of the documentation
Yes,
of the
sure.
integration, or like the live demo. Or so yeah, um, I think you pointed to, there was a link in your slides.
Yeah, no problem. Let me reshare my screen with that documentation. And live demo, it's a bit unfortunate is that our lab cluster is on maintenance today. So I'm not able to do a live demo, but we can definitely walk through the code of like which contains every single step you need to do to run the experiment. So let me share my screen. Can you see? So actually, here's our documentation. You can easily search it at APPFL.ai, and you can find this integration at our tutorials running APPFL using MONAI bundle. So here we have some acknowledgement and introduction. And here is how you can install it. So here we provide a way to install it from our source code, where you need to pip install with the MONAI option. And then we provide you the script to download the spleen CT segmentation MONAI bundle from MONAI Model Zoo by just running this scripts. And then we download the data. We provide a simple script, Python script to download necessary data needed to train the model. And you just need to run this, copy the script and run it. And then we can launch the server. So in our repo, we already have an example folder which contains everything you need to run this experiment. You just need to do Python gRPC run server and provide the existing configuration file, which is resides in MONAI server fed average to launch the server. And user can change to other fetch learning algorithms by using other server configuration files. So maybe let me show it as well. So if you see, go to our APPFL repo and go to examples, you'll see resources, configs, and MONAI. We provide you can leverage, we give you a lot of server algorithms such as server fed average M for and asynchronous like server fed compass, and it contains everything you need to run different fetch learning algorithms. And okay, with that, you have launched the server, and then you open two other terminal. For example, if you just want to run the simulation, you open two other terminal on your machine, and then in this case we launched two clients. You just need to run Python gRPC run client with a client 1 configuration and client 2 configuration, which also contains anything you need to launch the two client. And here we show the experiment results starting from the client are actually getting configurations. I think here I'm showing a fed compass algorithms log because you can see that everything is going asynchronous. So yeah, that's it. I think that you can leverage different types of algorithms easily by using APPFL to train MONAI models. And yeah, I think that's it. And if you are curious about how this configuration file works, how to set up your own configuration, actually you can go to our example notebooks and see FL configurations, and this will give you more information about how this configuration files should look like and what type of fields you need to fill out, you need to give to launch your own fetch learning experiment. And we do have a bunch of example configurations files for different use case, different data set, and different features. So feel free to play with our repository. And I would like to hear any other questions or anything you want to know, and I can point you to the documentation. And if we don't have that, I will definitely write a new documentation for your use cases. Any questions?
Thanks, Zilinghan. So it sounds like you had a pretty straightforward time in integrating the MONAI algo with the APPFL framework.
Yeah,
I wonder, is there any gaps you identified where we could improve?
It's a really hard question because it's really easy to do the integration. That as I said, like maybe we can briefly talk about how easy it is. Like, so if you go to our repository and see our trainer, if you see our MONAI trainer, it just contains 124 lines, which contains all the logging, even the logging logic. So we really love how the MONAI FL bundle design is interface, which extremely streamline the integration to our framework. And I believe, right, its integration to other framework will also be such streamlined way. So we appreciate how MONAI does its interface. It's awesome, we would say.
Okay, great. I think there was one to-do we discussed, right, on the federated statistics, which I assume it's currently not supported, is it?
Yeah. So actually, we can briefly talk about that, and it's one of our future work. It's like you can create it like a actually, as we mentioned, like how we can add like data readiness. Let me find out if I don't think we have a real-time show of that, but actually is that maybe let me show from the source code. Suppose we go to the configs, and then we go to the minutes DR, which is minutes with some data readiness. And here is how you can leverage data readiness in your experiment. So you just need to add data readiness config, and if you want to generate data readiness report, and you can select whatever metrics you want to use, like you want to inspect. And we will also try to integrate such features for the MONAI integration so that user can also see what is the statistic for the MONAI data set to get a sense of how the data looks like before you do federated learning. So you can make some smarter decisions before you really launch some GPU training jobs. So that's one of our tasks in our roadmap for the MONAI further integration. So we don't stop here. We will continue to improve it because we love like all the models provided by MONAI. So we want the user to have more capabilities when they are using our framework to train MONAI models.
Is there any update you see which would make this aspect useful? Is there anything in the MONAI framework which could be updated to make this data readiness metrics computation simpler, or do you think the current API is sufficient?
Yeah, I think like MONAI have like a MONAI Algo stat API, and I think that's is pretty much sufficient for make this integration happen as well.
That's excellent.
Okay. Any other questions?
I'm interested in your privacy preserving algorithms. I think you showed like one slide on that.
Yeah.
Can you remind me, was that a new differential privacy algorithm, or did you do something on the aggregation side?
It is actually called IIADM. It's developed by one of our mathematician in our group. So it's also supported in our framework. So if you go to algorithm, it's called an aggregator. It's called IIADMM, and we also have example configurations for those. So it is just like more robust to differential privacy losses. So
yeah, so it is it's kind of in the direction of robust aggregation, right? Where you can better handle the noise that is added by the differential private training.
Yes.
Okay. So clients do the differential private SGD. Is that what you do?
For the clients, you also need it has like a separate IIADMM trainer, so they have to work together.
Okay.
Yeah, to make that happen.
I wonder, so this is for the threat model here is to a malicious server that is attacking updates from the client trying to reconstruct training data. Is that correct?
Yes. So like suppose you don't trust the server, but the server say, okay, I will use this IIADM. So because like when you add differential add noise on the client local model, the server actually cannot reconstruct your data. But you say, but I still want good model, so please server use this algorithm because I don't trust you, but use this algorithm. It's kind of like this logic.
Right. So I think this kind of malicious server attack, right? There are other ways of getting around it without impacting the model quality, like homomorphic encryption or confidential computing, like trusted execution environments, right?
Yeah.
So I wonder if you have investigated what happens after the training. Let's say we use homomorphic encryption to prevent a server-side attack, but is there something that the model can memorize and leak information through its through the training? I assume your method would also help against that.
Oh yeah, I got you. You mean like for HE, right? You can prevent like attack during the training process, but after that, the model can memorize something that's you can continue to attack it after the training, but actually I don't think we actually investigate if this algorithm can have the capability to also prevent the attack after the training. But I think this is a good topic. This is a good research topic, and and also it's a good point of investigation of whether the model really have the like the method really have the capability of doing that. So yeah, my answer is like a question mark. Is hard to tell right now, but it worth investigation.
Yeah, if anyone knows about good ways of quantifying how much the model is memorizing, I think that could be interesting.
Yeah, there's this DP auditing. So I guess the homomorphic encryption, the ability to do this or this TEEs essentially mean that you can get away with only needing central differential privacy. You don't need the local differential privacy. And to quantify the central differential privacy, we can use the auditing framework. There's this I think it was one of the outstanding papers at last NewLips.
Oh.
It's a really cool method. It's called training differential. Yeah, let me find the paper and share it.
Is it something like I was thinking about like membership inference attacks and things like that?
Exactly.
Okay.
Yeah, it's based on the membership inference attack framework. But in a more principled way, like you can actually compute. You can get an estimate of you can get an epsilon estimate, not just membership inference attack percentage, but really translate that into a formal epsilon guarantee, or like an estimate. It's not a guarantee, it's an estimate. Yeah, I just shared it in the chat. Yeah, I think maybe this could be something for us to sort of look at next, like this data protection and looking at privacy, integrating some of these privacy techniques into the MONAI framework could be something interesting to do as a next step.
Yeah. Given that our main focus this year is on the data quality, right?
Yeah.
I feel like what Ziling showed with this data readiness report, maybe that's gonna be like a big win already for this year's aim, right? If we show that you can take the MONAI statistics and enhance it with what APPFL has built, write a little paper around it or something like that, and we have a big achievement already.
Yeah, absolutely. It would be still cool to I think explore some of the more advanced ways of doing this outlier detection kind of methods. Like maybe use
Right.
we were discussing these can we use embeddings from foundation models in some way to amplify some of this? I think, yeah, I suspect it should be pretty easy to extend the current like APPFL with MONAI statistics to just incorporate a pre-processing step with some foundation models there.
Right. Yeah, I guess we can directly send those statistics also over.
Yeah, and I think that would be a nice paper. Hopefully it works and we can showcase some interesting results. And yeah, I mean, that would sort of solve like that big goal for the year.
So maybe then there's some time left for addressing privacy as well. Are there other questions?
Yeah, I think we can also reach out to Zilinghan by email for those seeing the recording. Hopefully it'll be up on the website now. And
Thank you.
thanks so much, Zilinghan, for the talk today and as well as like the excellent integration. And if anyone in the working group wants to reach out to us to sort of be part of this integration, yeah, feel free to reach out and let's hopefully continue working on this.
Yeah, sure. Thank you.
Thanks, everyone.
I think we already have an agenda for next time, right? Is that has been confirmed?
Yes, that was the
ML Commons.
ML Commons folk, right? Yes, that's right. I'll send out the email today. Yeah, they did confirm it.
Okay. Great. Thanks, everyone.
Thanks.
Thanks,
Bye.
Zilinghan.
Take care.
Thank you. Bye.
Bye.